Welcome everyone to this new iteration of the GEOTOP seminar. Speaker today is Magnus Botnan, professor at Amsterdam, and he's going to talk to us about properties of flag complexes and multiparameter persistence in degree zero. Like Magnus, floor is yours.
All right, thank you, Mathieu, for introduction. Thank you to the organizers for inviting me to speak at this online seminar. And I will be talking about two separate projects. I couldn't really decide what to talk about, so I decided to talk about both of them, which are somewhat related through this notion of, well, extremality. The first project is then on flag complexes, as Mathieu said, and the second project is on multi-parameter persistence. So let's just jump into it. This paper is joined with Lise Theirs. It's on the archive. It's titled Extremal Beta Numbers and Persistence in Flag Complexes, and it was accepted to SoCG this year. So we will present this in Japan later this year. All right. So I suppose we are familiar with the notion of a VR complex, Vietoris-Rips complex, but it's a simplicial complex that's defined from a set of points in a metric space. So let's assume the point set is finite, and you form the connectivity graph where you connect any 2 points that are distance at most 2r, and then whenever you have, well, for that graph, you make the largest possible simplicial complex with that graph as its one skeleton. So if you look at the following, we see that we have 3 points that are all pairwise connected, and therefore you also add in a triangle because you can do it. All its faces are there. And likewise here, we add in a tetrahedron because we have all the faces as well. So the Vietoris-Rips complex is important in TDA, and it's an example of a flag complex, which I will return to momentarily. But let's just do a intermezzo into this beautiful figure by Robert Christ, where he shows how from a point set, in this case in the plane, you keep enlarging the connectivity graph, and then you form the clique complex, the Rips complex, the flag complex. And as the scale parameter increases, the complex grows, and you track the topology of the topological features. So we see here that you even have some H2 for a planar point set, but that's what can happen when you work with the Vietoris-Rips complex in place of, let's say, the check complex, which is topologically faithful. That said, the Vietoris-Rips complex is still what's used in state-of-the-art software. So it's certainly relevant. And a flag complex of a graph G is the largest possible simplicial complex with that graph as its one skeleton. So that means explicitly that if you have a m+1 clique, then you also have a m simplex. So when you have a 3 clique, so 3 points that are all pairwise connected, you also glue in the triangle. And likewise with the tetrahedra and so forth. So you can see how flag complex is closely related to the Vietoris-Rips complex. It's just that the flag complex is defined for arbitrary graph, whereas the Vietoris-Rips complex is a metric construction. Now, once you have a simplicial complex, you can talk about these reduced homology groups, and we will talk about reduced homology groups, meaning simply that these are the normal homology groups over some field, but in degree 0, a space will have homology 0 if it's connected. So the dimension of the kth beta number, which is just the kth beta number, which is just a dimension of the vector space, will be 0 in degree 0 when the space is connected. And we will use a shorthand notation, beta IFL, to denote the ith beta number of the flag complex of the graph G. So we just write G here in addition to the notation FL to highlight that we are actually taking first the flag complex and then the ith reduced Betty number. So in this case, we have a graph. We take its flag complex and it's connected. So Betty 0 is 0 and Betty 1 is equal to 2 because there are two holes. And these are examples of two-run graphs that will play a prominent role in this talk. And they have the additional property that at least when the second factor here is 2, then the flag complex will be equal to the graph itself because there are no 3 clicks. There are no 3 points that are all pairwise connected. Okay, so some related work to what I'm going to talk about today is a very nice work by Dmitry Kozlov, related to earlier work by Bauer and others, where they take a graph G, they take its flag complex, they assume that the graph has n vertices, and now they form any z-linear combination, or Kozlov forms any z-linear combination of the kth Betty numbers. And then he says, well, the extremal value of this linear combination is always obtained by a two-run graph. So I will get back to two-run graphs in a moment. I'm just highlighting their importance. And you can also do similar constructions with the number of simplices in each dimension instead of the Betty numbers. And still, these C-linear combinations will be maximized by some two-run graph. And perhaps the most natural thing to consider is then to take the sum of the Betty numbers in all dimensions and maximize this. So you have a graph, you take a graph, you take its flag complex and you compute this Betty number in all dimensions, and you add up those numbers. Now it follows by Kozlov's work that the graph that maximizes this number is a two-run graph. Adamaszek recovers this result using a different proof. And that paper is important to us because we leverage his ideas quite significantly in our own proofs. And what he shows is that it's precisely this two-run graph which maximizes this total Betty number. So I will define this very soon. It's not important to this talk. Okay. Now, so what they did was to fix a graph and maximize some topological property. So, I mean to fix a number of vertices and then look for a graph such that its flag complex maximizes some number. In our paper, our focus is with filtrations of flag complexes. We will consider edgewise filtrations. That means that we are growing the graph, adding one edge at a time. And obviously, when you have a filtration of graphs, you can form the flag complex at each step, and that gives you a filtration of flag complexes. Okay, now this is some filtration of topological spaces. We can take its persistent homology, and in degree k, we will use this script BKFL of script G notation to represent its barcode. So it's just the barcode in degree k homology of this filtration. And then the total persistence is when you take at each filtration step, for a fixed k, I'm only going to consider fixed k, you take the Betty number of the flag complex, the ith step in the filtration, and you sum those numbers over all filtration steps. That will be the total persistence. Now, equivalently, you can think about that in an edgewise filtration as being the sum of the lengths of the bars in some homology dimension. Okay. And in our paper, we had this small lemma, which is well known, but I'm not really sure what the good reference is, so we just proved it. It's like 4 lines. And without being too explicit about what precisely the lemma says, I will just mention its implication, which is that whenever you have an edgewise filtration of graphs, so adding one edge at a time, this can always be realized by taking the Vietoris, by the increasing neighborhood graphs of some point set. So all the simplicial complexes that comes from edgewise filtrations can be realized as filtrations of VR complexes. The VR complex is coming from data. So all our results can be realized by potentially highly synthetic, but notwithstanding data. Okay. So just to set the stage a little bit. So our main questions, Lisa and I, our main questions include how many topological features, or like broadly said, like how many topological features can arise in a data set of endpoints. So we investigate bounds on the following. So what is the maximal value of the BDK of a flag complex of a graph G, assuming that we have n vertices in the graph? So equivalently, how many features can be simultaneously alive in degree K homology? So if you go back to this picture here, if you take any vertical line, for instance, the line here, and if you count the number of green bars over that vertical line, you'll see 1, 2, 3. So that step, there are 3 H1 features alive. So the question is then, for any such time step, what's the maximal number of intervals that can intersect that vertical line if you restrict yourself to complexes of n vertices? Then we consider a problem of maximizing the number of bars of filtration on n vertices. We consider the longest possible interval, or the longest possible bar, so the longest living feature can be in data, and the sum of the lengths of the intervals, so the total persistence, like what's a total topology, maximal total topology of some data sets. Okay. All right, so now let's get to the Turing graphs. A graph is triangle-free if it contains no triangles. All right. So if you take the complete graph on 5 vertices, it's triangle. It's not triangle-free, certainly not. But any bipartite graph is. Okay. And in 1907, Willem Mantel, he proved the following theorem. Every simple n vertex graph with more than n squared divided by 4 edges has a triangle. Okay. And this implies that, and also if you're looking for a graph that has n squared divided by 4 edges and no triangles, then it has to be the complete bipartite graph if n is even. Okay. So put differently, I have n vertices. I would like to add as many edges as possible without forming a triangle. Well, then I have to put them into this bipartite form, and I can put precisely this many edges without forming a triangle. And this is the unique optimizer. Okay, this is not very hard to prove. But then to generalize this. So let G be a graph. A k-click is a subgraph of G which is a complete subgraph of G with k vertices. So an edge is a 2-click, a triangle is a 3-click, etc. And then you can generalize the idea of a bipartite graph to a tripartite graph. So in this case, we have these two versus the bottom here. They're in the same partition, so they're not connected by an edge. The top left, there are 3 vertices. They're also in the same partition, but they're not connected by an edge. And also the 3 elements of top right are in one partition. But all the partitions between them have all possible edges. So it's complete tripartite. No internal edges, but all possible edges between the partition. And Turan, he asked and answered the following question, which has some significant implications in graph theory. Which k+1 click-free graph on n vertices have the maximal number of edges over all n vertex graphs without k+1 clicks? Okay. Put differently, I have n vertices. I would like to put as many edges in that graph as possible, but I would not want to have a k+1 click. So equivalently, in the corresponding flag complex, I do not want to see any k simplices. As many edges as possible without any k simplices in the flag complex. And Turan here said that, well, if you would like to have this construction, if you want to maximize the number of edges, then the unique optimizer, up to some reordering, is the Turan graph nk. Okay, so if k is equal to 2, then we are maximizing the number of edges without triangles. So we're going to take the bipartite graph. So in this case here, we have to the very right, we have 8 vertices. And we would like to have as many edges as possible on any graphs on 8 vertices, but no 4 clicks, so no tetrahedra. Okay. And the unique way of doing that, up to some obvious reordering, is to put them in partitions like this. So it just means take your points, and if you want to maximize the number of edges without tetrahedra, partition your points into 3 partitions where you divide the vertices as evenly as possible. Okay, that's great. And now how does that connect to what we would like to do? Well, I mean, maybe there's an obvious connection. Like if you would like to maximize H1 in the Rips complex or the flag complex, you would like to have as many loops as possible, but no loop of length 3, because that would be a triangle. So you would like to have as many loops of length 4 as possible. In some sense, as many edges as possible, but without having any triangles, because triangles kill stuff, and you don't want to kill homology. Okay, so yet here are the 3 Turan graphs from before. And we recover Kozlov's result by adapting the work by Adamaszek by showing that of all graphs on n vertices, the Turan graph T n k plus 1 maximizes the kth Betti number. Okay, so if you want to maximize Betti 1, well, then you're going to build something that's bipartite. If you're going to maximize Betti 2, well, then you're going to maximize build something that's tripartite, etc., etc. Okay, so this also follows by the work by Kozlov, but this proof is fundamentally different. Okay, so that answers the first question we asked, actually. It's like how many features can be alive at any given step of the filtration? Well, that's a number of features in the Turan graph, in this flag complex. Okay, and then just to get a little bit of a feel for a Turan graph, this will be relevant later. So what is the degree 1 homology of these graphs? Well, we have them on to the left here. And then if you just unfold it a little bit, you push the vertex to the left and then move vertices around a little bit. You see that this is actually the same as this graph to the left, which clearly has Betti 1 is equal to 2 because there are 2 holes in this one. Note that there are no triangles. And to the right, a little bit more work, but you have 2 holes in the background. And make note here, this is important, that these edges do not intersect here. They pass on top of each other. So you have the 2 holes in the background, and there's 1 loop coming from the 1 diagonal edge going on top, let's say, and then there's 1 loop from the diagonal edge going at the bottom. So in the total here, there are H1 is equal to 4, not 6 as the image might suggest, because the graph is not planar. So we have 2 and 4, and in general, you have this expression for the first Betti number of the flag complex of a Turan graph with 2 partitions. So you can, if n is even, it's just n divided by 2 minus 1 squared. And this is known, obviously. Okay, and to see why that's the case, and we will also have this will be important in the latter discussion. So if you have a graph and you can partition the vertex set into 2, such that all edges from V1 are connected. Sorry, so all points in V1 are connected to all points in V2. Okay, so we have a complete bipartite spanning subgraph or something like this. Okay, I will show a picture. Then if Di is the number of connected components of Vi, then the Betti 1 of this graph is just the number of connected components in the one part of the graph, the V1, the restriction of G to V1, minus 1, times the number of connected components of G restricted V2 minus 1. Okay, so maybe that was not too clear, so let's look at a picture. Here we have these 4 vertices on the left-hand side and these 4 vertices on the right-hand side. So the graph has 8 vertices, and we see that everything is connected from the left to the right. Now, what does this tell us, this result? It tells us that the homology here is the number of connected components to the left minus 1 times the number of connected components to the right minus 1. So 3 times 3, so that's 9. In the middle example, we have 1, 2, 3 connected components, 1, 2, 3 connected components. So beta 1 is 4. And to the right, we have 1, 2, 3, 4 connected components and 1, 2. So in this case, beta 1 is equal to 3. So it's very easy to compute beta 1 for these graphs. This is cannot formula proof. It's not very difficult. Okay. So before I go to the total persistence, let us overview there is, well, at least one result we have where we have complete understanding in all dimensions. So if you take the K barcode or any edgewise filtration or graphs on n vertices, then a bar can never be born before you've added 2k times k plus 1 edges. And no bar can live past the point n minus 1 choose 2 plus k. Past that point, when you added that many edges, everything's dead in degree k homology. So as a sanity check, let's say if k is equal to 1, you want some h1. Well, then you need 2 times 1 times 2, which is 4 edges, because you need 4 to form a hole with no triangle. And what's important about the right-hand side here in the bound is that this actually happens before you have a cone in the simplicial complex. So this happens before. You can still have homology in other degrees, but in degree k, there will be no homology past this. This is tight in all dimensions. This is great. We're happy about this result. Now, for the maximum number of intervals, unfortunately, we only understand this, well, trivially in degree 0, but in degree 1 and not in degree 2. So what we show is that you can never have more intervals than the first Betty number of the Turan graph on that number of vertices. Okay? And this is actually unique. So if you have the maximal number of intervals in your filtration, then you are filtering the Turan graph. Then you're building up to the Turan graph. That's the only way you can have the maximal number of intervals in degree 1 homology. It's probably also the case in degree 2, 3, 4, etc. But higher degree homology is more complicated when working with Rips complex. I'll mention why later. Okay, so let's move to the total persistence. For a fixed number of vertices, which edgewise filtrations of the complete graph, so we're now assuming that we're going to add all possible edges, we go all the way to the end, maximize the total persistence, so the sum of the lengths of the bars. We don't know how to proceed with this problem. In general, it looks very difficult. Again, I will say something else later about this. But for the moment, let us focus on filtrations of the Turan graph. Notably, for k is equal to 1. Okay, so you may ask, of all filtrations of the Turan graph, which one maximizes the persistence? So for k1, k is equal to 1, this is equivalent to saying, okay, of all filtrations that have a maximal number of intervals, which ones or which one has the maximal total persistence? Okay, and this is the problem that we actually solve completely for k is equal to 1. And we think our result is important because the Turan graph is intrinsically interesting, but also because it is the maximal total persistence of any filtrations, like losing the restriction on the Turan graph. But we don't know how to prove that. I will come back to it as well. Okay, so what we do know is that when you're filtering your graph, adding edges, as long as you go up to the point where you need to have triangles for H1, we know everything. We can build a filtration like this one, and this one will have the maximal number of Betty 1, maximum number, the largest Betty 1 at every step of the filtration. So for instance, if you have 8 vertices and you want to have 6 edges, then you can never have more features than which is in the 6th step of this filtration. So that will be 2 bars alive. So this one has Betty 1 equal to 2. So these are all pointwise optimal. So our filtration is great we're always maximizing all the way up to the point where we hit the Turon graph. And this is not for only filtrations of Turon graphs. If you go up to 16 edges, it doesn't matter what you're filtering, you can never do better than this at any point of the filtration. But now we are at the point, thanks to Montel's theorem, that we know we need to add triangles. Okay? So we have this overview, and this actually holds in all dimensions. So we know precisely what happens up to the step where you have the number of edges in the Turon graph in any homology dimension. We understand this is just a green region, it's great. And this is for written for k is equal to 1, but it holds in general. Then we know everything that happens when you have enough edges, because then everything has vanished, because nothing can persist, because there's just too many boundaries. Now the danger zone is where you're maximizing homology, but you're forced to kill some homology because there has to be triangles present, or in higher degree homology, there has to be tetrahedra, etc., etc. And this is where it gets iffy. So we'll employ the following notation. So the join between two graphs G1 and G2 is the graph with vertex set, just the disjoint union of the vertices of G1 and G2. And where we include the edges in G1 and G2, and we add all possible edges between G1 and G2. Again, I will show a picture. And we know that in our filtration, once we pass the number of edges in the Turon graph, we will have the Turon graph as a subcomplex by definition, because we're filtering up the Turon graph and then we're adding more edges. So we know that we will have the Turon graph sitting as a subcomplex when we're past, like when we're entering the danger zone, let's say. And recall that in this setting, we can very easily compute the Betty1 by just taking the number of components in G1, subtract 1, times the number of components in G2, and subtracted by 1. Okay, so in this case, what this notation means, it means that you have these four vertices, you have the Turon graph, you have all possible edges between them, and then in addition, you have certain vertices coming from G1 and some edges coming from G1 and some edges coming from G2. And then we can compute the Betty1. It's very easy by just counting the number of components and multiplying them together once you subtracted 1. So in this case, you get 1 times 2, and Betty1 is equal to 2. Okay, so now let's go into the danger zone. So how are we going to proceed? And one way, so this is like really, now it's like really combinatorics, because what you're trying to do, in some sense, is to have a bag of edges, and you like to distribute the edges into this graph such that the product of the components, the number of components, is maximal. Okay? This is what you're trying to do, because this is how we compute the Betty number. Okay? But not only are you doing that, you're also doing that in a way that respects the filtration. And we show an example that when you're maximizing the total persistence, well, at some point, you have to make suboptimal decisions because you have to respect the filtration. So it could be that you have 19 edges, and the homology is larger than what we have after 19 edges, but then you have to make concessions later such that your total persistence comes out worse. This is really, I mean, the proof is super technical, inductive, lots of inequalities and topological combinatorics. Okay, so here's anyways one approach. You just add one to the left, one to the right, then you add one to the left again. And then, of course, if you can add one more for free without killing anything, because you only kill homology when the number of components decrease on either of the sides. So that makes sense. Okay, left, right, as many as possible to the left without killing, and then go to the right, etc. So now I add one more on the right, I add one more on the right for free, because nothing dies here. You can see nothing dies at 22, because we're just connecting something that was already connected here. And then at 23, everything vanishes because now there's one component, and then we know that homology is 0. So past 23, there's no homology. Okay, so that's one approach. Now you can try an alternative approach where you add more aggressively to the left-hand side. So first you add 3 here, and then you add 3 on the other side, and then maybe you add to get the click here, and then you add a click on the other side. Now you're not going to go a lot farther in this case because homology is died. But actually in these two cases, the total persistence comes out the same. So we tried a bunch of natural approaches and we computed the total persistence, but to our great surprise, the number came out the same. So like, what is this? Is it some funny combinatorics that we're missing? And then upon closer inspection, I found some example which suggested that maybe what we're doing is not optimal. So we ran computations and we tried all possible permutations for small examples. And this roughly came out to be the optimal. We have very little intuition why this is the case, that this is optimal. This is, I mean, the precise statement is rather technical, but it's essentially what happens. The best thing you can do is to take 3/4 on all the vertices on the left-hand side, let's say, and you form a click with them, like adding all the edges there in the smartest possible way, only working on one side. Then you jump to the other side and you add 3/4 of the edges there. And then you start adding 1 point to each side. So you add 1 point, connect all this to all below. You add 1 point on the other side, connect to all below, and then you alternate like this. This turns out to be the unique optimal way of doing this. It depends. I mean, there is like some mod, like some, depends a bit on the n, like n mod 7. No, sorry, n mod 4. But whether it's just a unique construction or if there are two that are similar but not entirely equivalent ways of maximizing the persistence. Okay, so basically, if you just go back here to our Turan graph, where we said, okay, what to do next? We are here, and you want to go to the end. So then you add on one side here 3/4 of the edges. So 3/4 of the vertices are connected in a click, and then you form a click here with 3/4 of the edges, and then you start alternating. That will give you the maximal total persistence in a unique way. Okay. So where are we now? Well, we're answering some, I think, fundamental questions in TDA, at least made some partial progress, because these are natural questions, and to my surprise, they haven't really been studied that much. Maybe they deserve more attention. It's extremality questions in TDA. And the good thing is that there are tons of open questions, and we have a few conjectures. And one reviewer said that the most interesting part of the paper was in the discussion part, the conjectures. So let's see what the conjectures are. The first one is very natural, and this has to be true, I think. But we don't. It's just you can't have more bars than the number of features in the Turan graph. And so we know this for k is equal to 1, but for k is equal to 2, we don't. And where it gets a bit tricky is that in degree 1 homology, if you add an edge, you can add at most one homology class. You can generate one additional homology class. If you do Betty 2, because you're doing the flag complex, you could add one edge. You can generate a bunch of new Betty 2, but you can also kill a lot of Betty 2. So how these things weigh up and add up makes k is equal to 2 much harder than k is equal to 1, I think. We think that the filtration I showed before for k is equal to 1 is globally extreme in the sense that there were all possible filtration, edgewise filtrations. This one maximizes degree 1 total persistence in the mole. It's extreme in all possible ways, as I said before. Maximal length of the bar, number of bars present at any point, number of bars in total, and total persistence. We think it's really the unique, most extreme complex. But it's a bit difficult because you can show that once you're in a danger zone, your whatever filtration you have can never always be pointwise optimal. So once you are before danger zone, we have to add triangles. Yes, we have always pointwise optimality, but that's not possible. So that again, you need to make concessions, respect the filtration, and then see how things add up. And it looks a little bit iffy. And it brings us to like very natural first stepping stone, And that's the question which generalizes the questions considered in the classical literature, where I would like to maximize topological properties, let's say some linear combination of the Betty numbers, for graphs on n vertices and precisely m edges. Because now, if you have m edges and m is large enough, you need to add triangles. And that complicates things. And you need to add tetrahedra, etc. So you don't even know anymore that, well, we have an example in the paper showing that in this case, when you're in this region, like in the danger zone, the graphs that maximize homology, they need not have a Turan graph as a subgraph. Okay. So it requires some new ideas, but I think it's a very interesting question that someone should think about. Well, I'm very happy to discuss this. Okay, and here's just, so our conjecture is that yes, whatever maximizes for n vertices and m edges will have a complete spanning subgraph, meaning that you have some partition into V1 and V2 and all possible edges are there. It's just that they don't have to be evenly divided like in a Turan graph setting. So in our paper, we have this approach. Well, following our approach, we also are able to give a upper bound using a computer on the maximal Betty one. And the x-axis here tells you how many edges you are past the point of the Turan graph. Like now you're inside the danger zone, so you know that homology has to start vanishing because you're adding triangles. So the orange dotted line is an upper bound, and the blue line is what you would achieve under our conjecture that whatever maximizes has a complete bipartite spanning subgraph. Okay, but even if you know what pointwise maximizes, figuring out that our construction is the one that maximizes total persistence seems to require some new ideas. Okay, so now I'm going to go on to part 2, which is completely different. I think it's a good time to stop and hear if there are some questions.
Uh, Thanks a lot for this very interesting first part. Is there any question in the audience for Magnus? I guess I can start with a naive one. Here you're studying homology groups over, so the Betti number, but using homology over any field, right? I'm supposing you're not
Yes.
assuming. So is there anything you can say about the torsion as well? Or
Well, so I think in the paper by Kozlov, he says that, well,
Mhm.
you can just do it. His construction is over integers, I think, because these extremal complexes, the Turan graphs, they don't have any
Mhm.
torsion.
Yeah, okay, okay, okay. All right.
So
Everything is in the free part. Okay, right.
yes, 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 yes.
Mhm. Yeah, I guess it makes sense. Right. And do you think there are other simple or well, I guess this is also probably a very difficult question, but given how complicated it is also to work with the total persistence, but do you think a linear combination of Betti numbers to rise to some power could also be manageable, or trying to find other functions of the Betti numbers that could also be maximized instead
Right.
of just their
So
sum? Well,
it's a
which
very
is already
interesting
hard
idea.
enough.
I think, yeah, well, I mean, so we have this question here,
Mhm.
right? So I mean, for Betty one,
Mhm.
I think it's good to start with this to
Right,
see if one
yes.
can
Right. Yeah.
maximize Betty one with a fixed number of edges and vertices.
Mhm. Mhm.
But so basically, what Kozlov does is to say that he recognizes that what he's trying to do is a linear optimization problem,
Mhm.
like linear programming, the C linear function. And
Mhm.
he embeds all simplicial complexes in a certain space. And then he says that since I'm doing linear optimization, I know that the extremal values will be at some corner point of the convex hull.
Mhm.
And then he
Mhm.
identifies the corner points as being the Turan graphs. At
I
least,
see.
I
Mhm.
think that's how it works. So one could try something like this, of course. I don't know. I mean, there's, as far as I know, this has not been explored, so there's a lot of fun things to
Makes
try.
sense. Uh, okay, I guess maybe if there are no other questions, we can get going with the second part, maybe.
Yeah, sure. All right, so the second part is completely disjoint from the first part, and I will mostly highlight our results because it's a little bit technical. This is really in representation theory. This is joint work with Uli Bauer, Stefan Oppermann, and Johann Steen, and it was recently put on the archive, and it's now submitted to some journal. So we'll see how that goes. And this is within the field of multiparameter persistence, wherein I do most of my work. And it's a fascinating field, the intersection of many different branches of math. I've seen quite a lot of progress recently, and there has been at least one, possibly multiple talks on multiparameter persistence on this seminar. So I'm not going to speak too much about the background here. But in general, the pipeline for multiparameter persistent homology is to construct a commutative diagram, so some diagram, graph of topological spaces and inclusions. And then you apply homology, you get a graph, directed graph of vector spaces and linear maps. And then you can try to look at this representation, this graph of vector space and linear maps, and see if you can extract something useful that you can use to infer something about the underlying data set. So if you're in the one parameter setting, you start with the filtered simplicial complex, like we just saw. You apply homology, and then you get what's called a representation of a quiver of type AM. It's not terribly important exactly what that is, but what's important is that such representations decompose into a direct sum of indecomposables, such that you can always change the basis, such that the representation looks like this optoisomorphism, and such that it decomposes into some of such representations optoisomorphism, and it's the support of these representations that constitutes, so that the supports constitute the barcode that we see in non-persistent homology. Now in 2D persistence, which is motivated by data with outliers, variations in density, time varying data, and so forth, you have a 2D diagram that in this indexes your filtration. And when you take an homology and you get the vector spaces and linear maps, you end up with a poset, which is of so-called wild representation type. And what that means in this case is that you don't know what the indecomposables look like. So you can always take your diagram, vector spaces, linear maps. You can chop it up into indecomposable pieces, but you don't know a priori what those pieces look like because you can't essentially you can't classify them. You can do it for a linear case because you know that they all will look like this, a isomorphism. But in this case, this is very complicated. So a well-known result in TDA, multiparameter persistence, is that if you take any diagram of vector spaces and linear maps, assuming that your prime is a prime field, so that a prime number of elements or the rationals, then every such diagram of vector spaces and linear maps can be obtained by applying H1 or H2 or H3 or whatever, higher dimensional homology to a bifiltration of a graph. Bifiltration of topological space. So if I would like to have this diagram of vector space and linear maps, then there's a way I can construct a bifiltered topological space, apply homology such that for the some choice of basis here of homology representatives, I will have this diagram of vector spaces linear maps. So for instance, in this case, we have like The outer circle would be then one homology generator. So it's K here, you have K squared, so you have outer circle, inner circle, and then you have another circle, so K3, still K3, but then you get K2 because this outer circle here gets completely filled in. Okay, I don't want to spend too much details on this, but any diagram you like, you don't, I mean, for any pole set, you can always realize it by applying homology to something that comes from topology. Now, what if you restrict your attention to H0? So basically what this says is that all the nasty algebra can be realized from TDA by taking some filtration of a space. Like all the indecomposables can be realized. You don't know what the indecomposables can look like a priori. There's no way of classifying the indecomposables that come from TDA. But what if you restrict yourself to H0? So clustering, you only look at connected components. And equivalently, you only look at bifiltrations of graphs or filtrations of graphs. Then if you do that to this example, you see here that there's K because there's one connected component, K squared, because there's two connected components, K squared, K, etc. And you can check that the linear maps, they come from choosing a specific basis. But all the matrices here, they have a very particular form, that every column has precisely one non-zero entry, and that entry is 1. So then you ask the question, are these representations well behaved? Is the representation theory any better? Because that would mean that, well, okay, maybe H1, etc. is difficult to multiparameter persistence, but H0, we can play around with that as if it were kind of like it was persistent homology in one parameter, because we know what the decomposables are. So just to look at a concrete example, let's say that we have the following 3 points, and we're adding these edges. Then we see that if you call them Q1, Q2, Q3, then a basis for H0 homology here is Q1, Q2. So Q1 goes to Q1, so you have 1, 0, 0. Q2 goes to Q2, so 0, 0, 1, 0. Here you have Q1 stays the same, but Q2 and Q3 get connected. So we can say that Q2 and Q3 get mapped to the same basis element. Now you can check that this will give you the following matrices, and you can do a change of basis. So if I think here I assume that I work mod 2. Yes, I work mod 2 here. Now if you change into these bases, then all the matrices diagonalize. So the first basis element go to the first basis element, goes to the first basis element, etc. And no two basis elements go to the same basis element. So every basis element either goes to a unique basis element and then inject away, or it goes to 0. Okay. And if you have that, then you can take this representation of diagrams, you can split it up into its components, because they're now they're always living in separate subspaces, they do not interact at all. And then sum out to coefficients with that basis is really isomorphic to these 3 components. Okay, so this Z2 here is just the point Q3 that appears here and immediately gets merged with something that was born before it. Okay, so whereas these representations do not come directly from applying H0 to a bifilter space, we say that they are additively realizable because they sit as summands of something that does. So more generally, we say that some representation is additively H0 realizable if it sits as a summand of some of applying H0 to a diagram of topological spaces. So our extremal question is, what are the additively H0 realizable representations? Okay. Now this seems to be very difficult to answer in general for grids. And one thing that we do show is that if K is a field of finite characteristic, okay, then the following representation, so you have 9 vertices and you have some 9 vector spaces and some linear maps. This is always an indecomposable representation. Then this one is additively realizable if and only if M is a power of the characteristic of K. So that kind of hints at understanding the H0 realizable representations is going to be very difficult. So A is here this bidiagonal matrix with forms type of Jordan block. Okay. So maybe for grids in general is hard, but we still make some progress. So we consider the additive image for an arbitrary small category. So if you like, you can think about just a pull set. And we ask, like, if you apply H0, are all the indecomposables, all the indecomposable representations of the diagram of vector spaces in the additive image? So can everything be realized as something coming from clustering? Are there only finitely many things that I can realize? And are, sorry, I misread the first. Sorry. So the first was, sorry, are all the indecomposables, that everything I can realize indicate the representations, meaning that can I only realize things like this, which have the underlying field connected by identity maps? Or do I only have finitely many things I can realize? Or can I actually realize everything? Now, of course, this will differ a lot from one category to the next one. So we make a lot of partial progress, is what I would say. The first thing you notice, the first result, and this is not too hard, is to show that if you look at the additive image of H0, that's the same as taking the additive image of the free functor from representations in set to vector spaces. So you have some diagram of sets and set maps. You apply the free vector spaces everywhere, free vector space everywhere. It gives you a new representation. And now if you take then the summons of this, it will give you the same additive image as for H0. Or you can also work with pointed sets and you get the same answer. Okay, so that says, okay, we don't have to care about topology at the moment. Let's just work with sets instead. So we're really studying representations that come from applying for the free functor to the set representations. And then we have a small lemma saying that if you have some representation which is indecomposable and it has a terminal vertex, and if the dimension of the representation of a terminal vertex is larger than 1, well, it doesn't come from set. So this one that we saw before by applying H1, this one, did we look at this? I forget. Or maybe, yeah, we did look at this one. Yes, we did look at this one. This one does not come from H0. There's no way you can realize this representation by doing H0 because the dimension of the terminal vertex is greater than 1. Like, somewhat surprisingly, even though it seems very difficult to classify these representations, we have an algorithm that it's exponential in the size of the field, but let's say you fix the field, let's say you fix the quiver, fix the diagram, then it runs in cubic time in the maximal vector space dimension of your representation. So if you give me a representation, then I can check if it comes from set or if it comes from clustering using this algorithm. Now, of course, for larger fields, this is not going to work. But for mod 2, we can do it for reasonably sized diagrams. And we show that if you're studying grids, which is most relevant to TDA for multiparameter persistence, that is equivalent to have like having infinitely many indecomposable representations are equivalent to having infinitely many additively set realizable indecomposable representations. Meaning that if you have, so you know that the representation theory becomes difficult when the grid is large enough. And when the grid becomes large enough, you also have infinitely many things that are additively set realizable. And yeah, and infinitely many things that are not additively set realizable. And this is basically where we are. We know that there are infinitely many things that you can realize and infinitely many things that you cannot realize. So did we gain much? Probably not. It seems like the representation theory is still very complicated, even if you restrict yourself to H0 and you do clustering. And then thinking a bit more only in the representation theory direction, we are trying to understand, like, if there is some like, well, okay, so let me just give this example and come back to what we're trying to understand. So this is what's called a 7-star quiver. And this is an example of a representation which is not additively centralizable. And I'm not going to tell you why, but we only know this because we thought it wouldn't be, and then we checked with the computer. We don't have a good argument for why it shouldn't be. We just know it because we did run our algorithm on this example. Now, this is a quiver, which is a wild representation type, and we know that it has a representation that's not added in the additive image. We know that if you go up to 4 edges going out, then everything can be realized, even though there's an infinite number of indecomposables. So we have for up to tame here, we can realize everything. But for 5 and 6, which is a wild representation type, we have no example of something that doesn't come from clustering, which is a bit surprising. So our conjecture is that if your quiver is wild, like very complicated, then there's always going to be something that doesn't come from H0 or from free. But we don't know how to prove that. And this is surprising because here you always have here you also have an infinite number of different indecomposable because it's a tame representation type. Everything comes from cluster. And just to finish, we wonder if the category of such representations has any nice properties. But when you look at D4s, like one central vertex and 4 arrows going in, then every single representation is in the additive image except for one. Meaning, we have that one thing in some AR quiver, like you have the representation theory, and then there's one representation surrounded by all the other representations, but that's the only one that cannot be additively centralizable or realized with H0. So that seems to suggest that there are no nice categorical properties, and we would like to understand this category better. Okay, so thank you very much for your attention.
Thanks a lot for the presentation. Any question from the audience? Not for now. Um, I myself am a bit curious about the algorithm actually that you designed for this. Do you, what's the complexity again? I think I missed that part.
It's well,
Okay,
depends.
okay.
So if you fix your quiver and you fix your field, then it's cubic
Yep.
in the vector space dimension. But that
And
may
it's
be cheating a
iterative.
little bit.
So I guess you go over every like uh,
No, it's not
or is it
iterative.
like the way it does it? Okay.
No, it's basically okay. So this okay, I can tell you what
Mhm.
the algorithm does. So you can take a representation,
Yep.
then you can take a forgetful functor. So you just think about it as being sets with set maps, and then you apply the free functor. So you take the
Mhm.
composition, first forget, then free. Then the representation is in the additive image of H0, if and only if your original representation M sits as a summand of free forget M. So I
Mhm.
take one
Mhm.
representation and I make it very large, and I check if my initial representation sits as a summand of this very large representation. And this you just then do it, or equivalently, there's a canonical map because the free and forget functor are adjoints. So there's a counit map. So you want to check if the counit map has an inverse, like a one-sided inverse that sits as a summand. So we use gap for this. So um, but that's basically that just comes down to solving like a huge system of linear equations.
Yeah, that's
And
the thing. In the end, it's all Gaussian elimination, right? So okay.
yes,
Okay.
yes, or a little bit lots of variables because you have all these matrices
Mhm.
that you need to fill in.
Mhm.
So so
I see.
yeah.
Interesting.
So
Like
that's a bit of a
okay.
problem is that so we actually for certain categories We know
Yep.
what the additive image is, but only because we ran the
Mm.
algorithm. We don't have a good categorical answer for it because it seems to be difficult.
So in practice, like how large or well, what's the I guess the maximum size you could handle with that?
So I have tried quite extensively to find some example. Like
Okay.
we can do this, right? But so I
Yeah.
looked a lot for examples of the five-star quivers, so five arms out instead, where something is not realizable.
Hmm.
And
Hmm.
I forget how maybe you can have 10 like if you sum the dimension of all the vector spaces, like maybe 100 or something like this.
Mm. I see. Okay, well, that's fun.
This is for mod 2
Roughly
though. I
speaking,
mean
I
for
guess.
mod 3 of
Mhm. Yeah. Or it could be mod anything. Is this also something that you can?
this so abstractly this holds for any field. But there's something
Right.
we
Okay.
mentioned in this discussion is like how can you is there an algorithm for this over the rationals, for instance? Because then you can't really take
Mm,
the
hmm.
forgetful
Mm.
function.
Right. Yeah, makes sense. Yeah, it's nice. Okay. Any other questions?
Yes, can you hear me?
Yeah.
Yeah.
Yeah, I had a question on the first part, but I didn't have a microphone then. Essentially, it was so you said that once you go beyond the number of edges that the Turan graph has, maybe the optimal thing to do isn't to well take the Turan graph and then add some extra edges.
Yes.
Do we know that if we want to maximize, say, the total persistence, like the sum of the length of the bars, do we know, do we have any reason to believe that it's the best option to first build a Turan graph and then do the best thing that we can? Or like, for all we know, could it be possible to do something suboptimal before the danger zone and then try to make up for it?
Yes. No. Yes. So I don't know. I think you, in some sense, it feels natural that you would like to generate as much as possible as early as possible, and so the only thing we know, right, concretely, is that once you go up to this point, then we're always optimal. We're always doing the best up to this number of edges.
Yeah.
Um, Past that, that's what makes it difficult, right? It could be that you actually do something stupid, so you start adding triangles here instead, because then that allows some features to live longer. So yeah, I don't
And
know.
like
I don't know.
experimentally with small stuff, do we find anything that's actually better than what you did, which I mean seems logical, but
No, no, we don't have any example. So we think that still the Turan graph filtrations to be the optimal, but we know in the paper there's a concrete example of sorry. So where's this graph? Like in this graph, we have 16 vertices, and then uh here I think let's see, I forget which one, but here is this number here. I forget. I think it's maybe it's this one. So if you take 20 edges and um, 8 vertices, then you can have Betty 1 equal to 2. But you cannot have this if you do the Turan graph, if the Turan graph is a subcomplex.
hmm.
So we have some example where the Turan graph, no Turan graph can be optimal. And so the first, I think, first natural step is to try to prove this conjecture that you need to have something with complete bipartite spanning subgraph. Now, if you go to degree 2 homology, etc., then you need to have some more lemmas because um, because we're in Betty 1, we have pretty good control over what Betty 1 is for such graphs. But for Betty 2, things are a bit more complicated.
Yeah, thank you.
Sure.
Any other question? All right, I guess if there is none, I guess we can end up here. Thanks a lot again, Magnus, for the very interesting talk. And thank everyone for attending.